Okay, so here's the review of the final exam. It really was called Exam 3 for mechanisms. It's a machine design topic, but we covered it towards the end of mechanisms. And here we go. Here's the first part of the problem, and I don't need to read it for you, but it's a fatigue problem. And it has a notch, and we want to make sure that we get the stress concentration for this part right here and include the notch sensitivity. So the first part of the problem asks for the Langer, the Soderberg, and the modified Goodman lines. Well, to be able to do that, we need to make sure that we have collected information on this steel right here. And if we look up in the back of the book, we will find that the yield strength for this AISI 1020 hot rolled steel, the yield strength is going to be 30 KSI. And we'll find that the ultimate strength is, did I say stress before? I meant strength. The ultimate strength is 55 KSI. Okay. We're going to need to know that. Oh, by the way, it's given that, it is given right here. Okay, well, we didn't need to know that. We also know that the fully corrected endurance strength, that's SE, is going to be 19 KSI. So I was nice enough to give you all that information. You didn't have to look it up in the appendix, but you could. You'll be expected to be able to do that. All right. So with that information, we go to a graph that I had provided for you. And first, let's take a look at the Soderberg line. Let's take a look at the Langer line first. The Langer line is simply the yield strength to the yield strength. So this grid is not proportional. The y and the x-axis are not proportional, but it doesn't matter. So that's okay. So I'm going to actually use a straight edge to draw between there. And I might as well change the color as well. So I'll go to red for the Soderberg. Both the Soderberg and the Goodman start out at on the y-axis, on the alternating, with SE, right? So that's going to be that point right there. Now the Soderberg, it goes to the yield strength on the mid-range. So we'll draw that one in. Whoops. Wanted to add in a little bit thing for me. Okay. Now we'll change colors again, and we'll put in the modified Goodman. Let's go with green. Green's nice. And we use the same point here on the alternating stress, but in this case we use the ultimate strength right here. So in terms of what the modified Goodman is, you could actually say, and I'll make this something light. Let's say I'll go a very light gray, and I'd color in this portion right here, but the Langer sort of chops off the modified Goodman. Okay, so this is the Goodman up from this point to this point, but the Langer cuts it off. All right, so that's the first part of the problem. The next part is to calculate the mean and alternating stress. So the mean stress, or mid-range stress, is really just the average. All right, I guess I'll stick with red. It's really just the average of the two stresses, right? So you could either do the stresses or you could do the forces, all right? So I'm going to actually calculate the mid-range force, because we're told that it fluctuates between 20,000 pounds and compression of negative 5,000, right? So I'm going to make sure that we use the correct signs, so that the average force, or the mean force, probably don't want to use average because we get confused with an A subscript, is going to be 7,500. the alternating is going to be the absolute value of the maximum minus the minimum. See, well, that's where the sign convention can be a little bit of a trick right there. I don't mean to ever use a trick, but it could be considered a trick, I guess. Just have to be careful that compression is negative, but we're subtracting it. So it's actually the alternating is going to be greater than the mean. Now, we're going to find the stress from these, but we got to do something first beforehand, all right? So let's put those to the side for a second and take a look at the stress concentration factor, so we can use the correct area for the stress. That's something we're going to check. All right. So the radius of our notch, right, that's at, or the radius of this fillet right here, is given as 0.4 right here. Okay, right? So the R over D that we're going to need to find right here, and for our stress concentration factor, is going to be 0.4, and that's going to be divided by this width right here, which is given as 3.375. And so we're going to get 0.1185, which I would go 0.1185. This would be 0.125. So somewhere in the vicinity of like right here, perhaps. Okay? And then we also need to know what the big width over the little width, and I know that's a little strange to use D, but that's how the figure is labeled, and that's 3.75 divided by 3.75, so we get 1.481. That's pretty close to being 1.5. So let's take a look at where it's at 1.5, and if you were to try to go in between here and take a look, well, your pencil width isn't all that great, but you end up with just about 2.0. So we'll call the theoretical stress concentration 2.0. Now, we also need to modify this for fatigue. We need to find out what the Q is. That's the notch sensitivity, and we could put it into the equation where it's this Q times the stress concentration factor, the theoretical one, minus by 1, right? So we're going to put it into there. Now, our notch radius was 0.4. That's pretty big. Well, what it says in the book is to just use the largest one right here. Okay. And we take a look at our ultimate strength, and our ultimate strength is 55. So that's pretty close to 60, maybe a little bit. It's kind of hard to extrapolate down below. There is an equation that you can use. Now, I wouldn't expect on an exam that you'd use the equation, but if you use the equation, you end up finding, well, I guess we would say anyway that it's going to be close to 0.8. Okay, so I was about to say that I used the equation, but in my answer, I just said close to. I use little squiggles. We could use little squiggles right here to say that it's approximately 0.8. So if you plug those guys in there, I don't need to do the step-by-step math for you. You get 1.8. Okay. Now you have to use the correct area for using this stress concentration thing, and that they say that they need to use this little d, not this big D, but this little d times the thickness. So the area, and sometimes they go A subscript 0, or is it O? I don't know. D times T, which is going to end up to be 3.375 times 0.375. You get 1.266 inches squared. So we find that the what we're going to use, we're going to find that the mid-range stress is going to be the fatigue stress concentration factor. That's what this guy is, times the mean nominal stress, and so that's going to be 1.8 times 7,500 that we found previously, divided by that 1.266, and you end up with a I'll just go ahead and make it into KSI, 10.67, and I'll squeeze in KSI here. And we find that the alternating is going to be similarly found with the correct forces, and we find that it's going to be 17.78. I just want to mention to you that there is a discussion in the text that describes in some times you do not use, for the mid-range, you don't use the stress concentration factor. I believe the convention is that if you get near the plastic range, then you go ahead and you don't use the stress concentration, because I believe the rationale, is that you'll have sort of a strain hardening, or when you have a little bit of plastic deformation in the in the notch. So then the notch doesn't matter as much in the mid-range, right? Because you could think of the mid-range as being the constant stress, or constant stress that's being put on the piece. Now the next part of the question asks for the safety factors for Langer, Soderberg, and Goodman. All right, so the Langer is just as you'd expect. It's the yield strength divided by the alternating plus the mid-range, because you could think of when at some point at the extremes the alternating and the mid-range are going to be added together. So that's what the large stress is going to be. So if you add those together, put those together, I'll go ahead and put the numbers here, but I'll leave them out in the next ones. I don't need to waste your time with writing out numerical stuff. You get 1.054. Okay. Now for the Soderberg, sometimes I just go solder as my subscript. We go 1 over the alternating as a ratio of SE plus the mid-range as an alternating of SY. Now, something to notice in terms of the equation and the diagram is that if you recall, we plotted our Soderberg on the alternating, we had SE as the point, and on the horizontal we had the yield, right? So we made those things together. Well, look, we have this, we're taking the ratio of them and the ratio of these, so that you see that they match, and then we're taking the inverse of it. So you could see that this is sort of just a graphical thing, but I don't need to, I'm not going to draw out the stuff for you. So we can find that is 0.774. All right, so it's less than 1. So in one respect, we can think, oh, it's failed the Soderberg criteria. But it hasn't actually failed, right? All it means when it has less than 1 is that it doesn't have infinite life, right? So that's not necessarily a horrible thing. It's just not infinite. All right, and notice with the equation here for the Goodman, just likewise, we used SE to compare the alternating, but we used ultimate for the Goodman. So we see that that's how it's arranged, and so we get 0.885. Right, now let's go back and plot those points. Right, it's a pretty important thing. Okay, well, we can plot out the point that we had with our stress was the alternating was found to be 17.78 KSI, and the mid-range was found to be 10.67 KSI. So if we were to plot a point like that, it would be somewhere along the lines, would be close to the 10, right, and 17 would be a little bit more, 17.78 be a little bit more than halfway. So let's say that it's like right here somewhere, right? So if we had a load line, and I'll switch to blue maybe. If we had a load line that would run through there, it would be from 0 right here to like that right there. Okay, so that's the load line. So things to note is that the intersection of the points right here. I'll try to use orange. I don't know if that'll show up. Okay, yeah. These intersections, if you compare the line to where the point is, this is where the point of our stress point is. The length to the line and the length from 0 to the stress point, the ratio of those is actually the safety factor. So you'll notice that in this case, the line here is longer than it is to the line to the stress point, and therefore the safety factor is greater than 1. And conversely, the line to the stress point is larger than the line to the Goodman, larger than the one to the Soderberg, so the safety factor is less than 1. Okay, so that makes sense. So now the last part of it is we're going to try to use the Goodman criteria to find what the equivalent completely reversed stress is. Well, first off, we can actually do that graphically. We're going to find it with numerically, but we could find it graphically. And what it is just like the Goodman, we use the ultimate stress, the ultimate strength, this point, but instead we pass through the stress point right here, right? And we can find where it intersects. That's the equivalent completely reversed stress. We call it sigma rev, right? So let's actually calculate that, right? So in the calculation for the reversed, and this actually comes from an example, it's not like written out, easily found in Shigley, is the alternating stress divided by 1 over the mid-range stress divided by the ultimate stress strength, and we find that it's 22.06 KSI. And that completes the problem here.